Welcome to part 3 of my video series, Covariant Compactification, Progress Towards a Theory of Everything Fundamental. If you haven't yet watched part 1 and part 2, you might want to do so before watching this. This talk is pitched at active physics researchers. However, there's plenty of material aimed at non-specialists on my website, Warped and Broken. If you'd like to support this physics research, you can do so by subscribing to my page on Patreon. There are currently 3 levels of subscription. The first level costs less each month than a cup of coffee or pint of beer in many cafes and bars, in UK currency just £4 plus VAT. With the second, at £15 per month plus sales tax, there's an option to be named on videos such as these. The most exclusive, at £100 per month plus tax, includes an option to be in a monthly group call with me and other patrons in this tier. My Patreon page includes both posts which are accessible to the general public and ones aimed at physics students and researchers. My ResearchGate page provides access to my various academic outputs. This is the third of a 5-part series. I'll start with a quick recap of what we covered in parts 1 and 2. The first section of the video explained the scientific motivation for the program of research which became covariant compactification. I then provided a rapid-fire 9-minute summary of the findings as they seem to me at this point. I'm now intending to extract this and the final section of part 1 and update them and turn them into a separate video. In the remaining section of part 1, I then moved on to the key high-level concepts of the theory which are necessary to introduce at the beginning if you're to understand the contents of part 2, this video, and the 2 forthcoming ones. These weave together into a conceptual structure for the theory. The second video in the series starts by looking at diffeomorphisms on spacetime, tangent fields, and their covariant derivatives. It considers product spacetimes and how certain components of the spin connection on these can be identified with gauge fields, and provides 2 examples of this. In the final section of part 2, I derived 2 field equations for the tangent fields and look briefly at cosmological implications. In this video, we move on to considering fermions. We show that a single generation of fermions, with its known quantum numbers, can be represented as a 32-component spinor of SO110. This is composed of 2 16 spinors of different spin states. Before they've acquired mass, they don't have the spin quantum number, and hence only one 16 spinor is needed. We describe how these 16 spinor states can arise as harmonics on the product of a 3-sphere and a 6-sphere, the spatial part of our vacuum geometry. We then go through the calculations in detail for the 3-sphere. First, we look at how the relevant groups act on the coordinates on the 3-sphere. Then we look at the transformations these induce on fields, showing that there are 2 pairs of harmonics which transform as the defining representation of SU2 left plus SU2 right. These can be expressed as the product of 2 factors. We find explicit forms for one of these factors. I then explain how I've tried to find the other factor, but encountered an apparent inconsistency I can't yet explain. We then expand the group of rotational diffeomorphisms to include improper rotations. Under this larger group, the 4 harmonics form a single representation. We show how an arbitrary spinor of SO4 can be expressed as a linear sum of these. We consider their continuity in reality and look at translations in this model. We then move on to diffeomorphisms on the 6th sphere and on its flat space limit. we explain how rotations on a sixth sphere induce an SU4 mixing of its harmonics, which contains color SU3, and how our model sits in a loophole in O'Rafferty's no-go theorem. In the final section, we look at symmetry breaking. We postulate the sterile right-handed neutrino is a background field. We show that its invariance group is precisely the standard model gauge group of weak isospin, weak hypercharge, and color SU3. We therefore view other quark and lepton states as perturbations away from this background. We close the video by taking a wider overview of symmetry breaking, including the Higgs mechanism and the factorization of spacetime described in Part 2. We start by counting the number of states in a single generation of fermions, compiling them into a single spinor, and stating the forms of the Lorentz and gauge group generators necessary to give these their known quantum numbers. We provide two forms and consider how the spinor decomposes when we use the second of these. This is the only section of this video in which we consider the action of the Lorentz group. After this, we'll focus on harmonics on compact spaces at a given moment in cosmic time. In Part 2, we just looked at gauge fields. These need matter fields to interact with, i.e. fermions. Before we discuss how these might arise, let's consider a single generation of fermions and the properties of its components. Counting up the combinations of spin, chiralities, colors, and isospin, we find that there are 32 states in total, including right-handed neutrinos. We can hence assemble them all into a 32-component spinor. The dimensionality of a spinor depends directly on the total number of physical dimensions. 32-component spinor can only arise if n is either 10 or 11. We can then use the quantum numbers of the 32 first-generation fermion states to find the 32-dimensional generators of the Lorentz group and electroweak and strong gauge groups. The forms of these I've given in previous presentations, for example, the Symmetry 2023 conference and the Minkowski meeting 2025, are as shown here in Kronecker product notation. Note that the color SU3 group is embedded in an SU4 group. However, at a late stage in preparing these slides, it's come to my attention that this embedding of color SU3 in an SU4 gauge symmetry also occurs in both the Patti-Salam model and George I's SO10 grand unified theory. Indeed, since I published part 2 of this video series, I've realized that my analysis had very nearly reproduced that of the SO10 gut. To put it into complete alignment, I needed to reorder the factors in the generators. Once I'd done so, the electroweak symmetry group fell out of the analysis in a very natural manner, and the chiral SU2 group it's contained in has a clear geometrical interpretation. The price of this is that the Lorentz boost and rotation generators have a non-standard form. The generators now have the forms shown here. Now, the final factor relates to the 6-dimensional compact space of extra dimensions, and the second and third factors relate to the cosmic compact space of our familiar three spatial dimensions at a given instant in cosmic time. And the first and second factors relate to a local inertial frame in 4-dimensional Minkowski spacetime. Let's look at some features of these. All of the generators generate transformations which act directly on the 32-component spinor. All 32 components are needed to describe massive fermions, that is, fermion states after the Higgs mechanism has endowed them with mass, along with any dressing from interactions with the gauge fields. This 32 component spinor is composed of two 16 spinors of SO10. One of these represents spin-up fermions, the other represents spin-down fermions. The SO10 corresponds to the 9 spatial dimensions in our model, plus the extra dimension used for embedding them. Each of these 16 spinors has two chiralities, the second factor in the Kronecker products, and two isospins, the third factor in the Kronecker products. This isospin is a quantum number of the chiral SU2 cross SU2 group. It's broader than either weak isospin or nuclear isospin in that it acts on both left and right-handed spinors and acts on both quarks and leptons. This chiral transformation, as we'll see, is induced on harmonics by rotational diffeomorphisms on 3-space. Note that for massless fermions, that is, before the states have acquired a mass, there is no spin quantum number. Instead, they have helicity, which is equal to their chirality. We therefore only need a single 16-component spinor to describe these. All of this allows us to decompose the spinor into fourplets, which are harmonics on the 6th space of extra dimensions. These fourplets contain the 3 colors of quark and a lepton, or in the case of the left-handed spinors, the antiquarks and antileptons. A rotational diffeomorphism on the 6th space of extra dimensions induces an SU4 transformation which mixes these. They transform as the defining representation of SU4 or its conjugate. The SU4 group therefore contains the color SU3 as a subgroup. It commutes with the Lorentz group, as expected, and indeed there is no overlap in their actions. On the other hand, the fact that the chiral factor pertains to both the action of the Lorentz group and the SU2 SU2 chiral group is the source of the parity violation of weak interactions. For clarity, it seems prudent to express each of the generators in block form as they act on the relevant spinor multiplets. As mentioned previously, the boost and rotation generators have non-standard forms. This is because both in the Dirac rep and the Weyl rep of the Clifford algebra, the chirality factor is superior to the spin factor. It has the bigger blocks. These forms for these matrices are what happens if you take the matrices in the Dirac rep and swap these factors over. As we'll describe shortly, the waveforms of the massive fermions can be written as a product of two factors. One of these factors ensure that they form a fundamental multiplet of harmonics on the 3 space, and this transforms very simply under weak isospin and weak hypercharge. The action of rotational diffeomorphisms on this space mixes left-handed spinors as one submultiplet, and this mixing is weak isospin. They also induce an SU2 mixing of right-handed spinors. Weak hypercharge generates the third component of this SU2 group. The generators of these SU2 groups commute with the Lorentz generators as required. The other factor ensures that the fermions form a fundamental multiplet of harmonics on the 6th space. The weak hypercharge also acts on this multiplet. We'll see why in the last section of this video. It acts on the lepton state. Its action on the lepton state is 3 times that of the action on the quark states, in the opposite direction. Again, this will be explained. The SU3 color generators only act on the quark states as expected. We're now going to see how these spinors can arise in a purely geometric theory in which the only entity is a curved spacetime. We'll start with a fairly heuristic overview for each of the 2 factor spaces. As implied in part 1 of this series of videos, spinors can be found by looking at how root mod G can be expanded in harmonics on compact spaces in our classical vacuum. Now, our classical vacuum is the Cartesian product of 2 factor spaces, DS4 and S6. S6 is compact, but DS4 is not. At a given instant in cosmic time, though, the spatial dimensions form an S3 subspace. We'll therefore look at harmonics on S3 and S6. The connected parts of the isometry groups of these spaces are SO4 and SO7. The keys to understanding the harmonics are the spinor representations of these connected isometry groups and the maximal unitary subgroups of these representations. We've already seen how the 32-component spinor can be written as a product of 2 factors, an 8-component spinor and a 4-component spinor. The isometries, their spinor representations, and their unitary subgroups allow us to show directly how the desired quantum numbers arise from the geometry of the 2 factor spaces. Let's see this first in outline for S6, then we'll go through it in detail for S3. The connected component of the isometry group of diffeomorphisms on S6 is SO7. This has an 8-component spinor. Within this, there's an SO6 subgroup which acts linearly on the coordinates on S6. The 8-spinor of SO7 is the direct sum of the 2 4-spinors of SO6. Now, SO6 is homomorphic to SU4. This homomorphism plays out through its spinorets. The 2 spinorets of SO6 generated by the same space of 4x4 traceless emission matrices as the defining representation of SU4. We'll see that this means an SO6 diffeomorphism on S6 drags the spinor fields round in such a way as to mix up their components, with the resulting spinor components related to the previous ones by an SU4 transformation. As for S3, its isometry group is O4. The connected component of this group is SO4. This has two component spinors. These are mixed, indeed they're swapped over, by the parity operator of O4. Just like SO6, SO4 has a homomorphism which plays out through its spinorets. Each of these spinorets is generated by the same space of 2x2 traceless Hermitian matrices as the defining representation of SU2. Thus, an SO4 diffeomorphism on S3 drags the right-handed spinor field round in such a way as to mix up its components, with the resulting spinor components related to the previous ones by an SU2 transformation. Likewise, it drags the left-handed spinor fields round in such a way as to mix up its components, with the resulting spinor components related to the previous ones by a separate SU2 transformation. Let's see this situation for the three-sphere in more detail. We'll start by showing how four Cartesian coordinates can be constructed from two pairs of two complex coordinates. We'll see how SU2 transformations on these pairs result in SO4 rotations on the Cartesian coordinates. Any field on S3 can be decomposed as a linear sum of harmonics. These can be grouped into multiplets of SO4. That is, each transforms as a unitary representation of SO4. All of these multiplets can be constructed from the two fundamental multiplets, the Spinor doublets and their conjugates. Analysis by Janssen in a paper from 1978 shows that all the harmonics, including the spinors, can be labelled by the quantum numbers associated with the two commuting SU2 subalgebras of SO4. What we do, therefore, is as follows. We look at rotational diffeomorphisms on S3 and identify the associated SU2 left and SU2 right transformations. We then look for a set of four fields over the coordinates on S3, which, under these diffeomorphisms, are mixed up as doublets of SU2 left across SU2 right. We'll also be interested in their transformations under parity. Janssen's starting point was to embed the three-sphere into four-dimensional Euclidean space, and then embed this space into the Lie algebra of U2. We'll modify this approach. To highlight the relationship between SO4 and its two separate spinor representations, we'll instead embed the four Cartesian coordinates in the Clifford algebra of SO4 using the four gamma matrices shown here. This is the Weil rep of SO4. Explicitly, the matrix in the Clifford algebra resulting from the embedding has this form. We now take a set of complex coordinates in the form of a pair of complex 2 vectors and their adjoints. Our embedding relates combinations of these to the Cartesian coordinates. We take their symmetrized outer product and then by comparing this with the first matrix, we find the relations we're after. This will allow us to find the action of the SU2 groups on the coordinates and ultimately on fields on S3. It's the complex coordinates that the SU2 groups generated by the subalgebras of SO4 act on. These actions have well-known explicit forms shown here. Using these and our relations between the complex coordinates and the Cartesian coordinates, we find the change in the Cartesian coordinates of each point on S3 under the diffeomorphism corresponding to each SU2 transformation. We'll focus on those generated by a single generator, the one-parameter subgroups. These expressions are fairly messy, but our initial interest will be in the rotations generated by the third generators of the two SU2 subgroups, those in this last column. As we'll see shortly, we can find much simpler transformation laws for these if we adopt an appropriate set of angular coordinates on the three-sphere. If we act on the complex coordinates with the same elements of both SU2 groups, the action on the symmetrized outer product is by conjugation. The corresponding diffeomorphism on S3 does not change the x4 value of any point, or the length of the position vector in the x1, x2, x3 hypervolume. This is therefore an SO3 rotation that stabilizes the x4 axis. In general, any action of the SU2 subgroups on the symmetrized outer product preserves the radius of the sphere, which we'll call ρ. These can be reduced continuously to the identity. Therefore, SU2 transformations on the complex 2 vectors induce SO4 diffeomorphisms on S3. We now define a new set of coordinates on the 3 sphere that will help us find harmonics. From the table of transformations under SU2 left and SU2 right that we found on the last slide, we can identify that each one-parameter subgroup induces a rotation in a pair of planes. In particular, T3 right and T3 left both induce rotations in the x1,2 and x3,4 planes. Therefore, we define a pair of polar coordinates for both of these planes. In these coordinates, we find that the squares of the two radial coordinates sum to the distance from the origin of the Euclidean four space, which is fixed for our 3 sphere. Finally, we use this to define an angle of rotation between the two planes, alpha. These 3 angular coordinates are independent, and changing them preserves ρ, so they fully parameterize S3. Note that we have chosen them so that they all reduce to 0 at the point stabilized when the elements of SU2 left and SU2 right are equal. Then theta and theta tilde transform very simply under the transformations generated by T3 right and T3 left, while alpha is invariant under these. Theta and theta tilde range between 0 and 2 pi, while alpha ranges from 0 to pi. We now want to use our new set of coordinates to find a set of 4 complex harmonics which transform as spinors of SO4. These will be functions of all 3 angular coordinates. I've managed to find the functional dependence of each of the 4 harmonics on 2 of these. However, for the dependence on alpha, an unexpected result has arisen, which I'm still trying to make sense of. It should be noted that this issue doesn't arise from trying to connect the mathematical theory to known physics. Rather, it's purely a problem in mathematical theory, more specifically in applying the theory of harmonics to a particular example. Despite this apparent inconsistency preventing completion of this analysis, the principles behind this section and the next should demonstrate to the viewer how linear sums of harmonics of a purely geometrical quantity can transform as a spinor field. Having found useful angular coordinates on S3 and how they provide a simple description of diffeomorphisms induced by the SU2 groups, we can now make full use of them. Recall that we were aiming to show how spinors can arise in the harmonic expansion of a single component field such as root mod G. Let's take an arbitrary one-component field, which we'll call phi. This is an arbitrary function of our chosen coordinates on S3. We now look at the action of omega-3 right and omega-3 left on this field. Remember that a diffeomorphism on a manifold is a map from each point of that manifold to a point on the same manifold. Such a transformation can induce a map on a scalar field by dragging the field along with it. This creates a new field configuration, which we'll call phi primed. For example, under an SU2 transformation parameterized by omega-3 left, point with coordinates alpha, theta, and theta tilde is mapped to another point whose theta and theta tilde coordinates are both reduced by omega-3 left over 2. This means that the new configuration at a point with coordinates alpha, theta, and theta tilde has the same value as the old configuration at a point whose theta and theta tilde coordinates are both increased by omega-3 left over 2. This allows us to Taylor expand the new configuration around the old one. Note that the Taylor series can be rewritten as a power series in a differential operator. Thus we see that the mapping of the field is generated by this operator. Using the same reasoning, we find that the dragging action of the group with the parameter omega-3 right is generated by this operator. If we have a set of such fields, phi alpha, they will all be dragged around in the same way. Now we expect our spinor fields to transform according to the spinor rep of SO4, that is, the defining rep of SU2 left plus SU2 right. If we again consider as an example the subgroup of transformations under the third generator of SU2 left, we get a similar expansion in this generator. By comparing this with the last equation on the previous slide, we find that the action of the differential operator is to mix up the spinor fields in the same way as multiplying them by the generator matrix. Now we expect our spinors to have quantum numbers associated with the commuting generators T3 left and T3 right. That is, they should be simultaneous eigenstates of both generators. We therefore look for simultaneous eigenstates of the corresponding operators. These are easy to find. They can be written as a product of two factors, the first being an arbitrary function of alpha, and the second being a function of theta and theta tilde, in which the only other parameters are the eigenvalues themselves. For the left-handed spinor, the eigenvalue IL is plus or minus a half, while IR is 0. For the right-handed spinor, it's the other way round. This is exactly what we'd expect from the eigenvalues of the generator matrices. Feeding these values in, we find the dependence for our fundamental spinor configurations on theta and theta tilde. These represent left-handed fermions with isospin up and isospin down, and right-handed fermions with isospin up and isospin down. To find the alpha dependence of our fundamental spinors, we should be able to use the action of the remaining generators on them. I've tried this for I1 right, and this is where things haven't turned out as I expected. These calculations are very recent, although I think I've seen this problem in various forms for about a year, and I'm still trying to figure out what it implies. In our angular coordinates, the operator has this form. Applying it to the right-handed doublet and equating it to the generator matrix operating on that doublet gives us two coupled equations. If we choose the A factors to be an appropriate trigonometric function of alpha, so that their derivatives are cot 2 alpha times those factors, then the trigonometric expressions on the left of our coupled equations collapse into exactly the same exponentials of theta minus theta tilde that appear on the right-hand sides. This is exactly what we want, the theta and theta tilde dependencies being equal in these equations. Unfortunately, if we divide through by these factors, the equations that we're left with are incompatible. Together, they imply that cot 2 alpha is imaginary. Note that even if it were a real constant, this would be a problem. It would imply that alpha could only take specific constant values. If this were mirrored for the left-handed spinor, there would be no way of constructing higher harmonics representing composite fields which vary with alpha. This would make a harmonic expansion of a field which varies with alpha impossible. We've now completed the bulk of our considerations of how harmonics on S3 can transform as spinors. But before moving on, we have a few more issues to consider in order to make contact with known physics. First, we want to expand the action of SO4 to the full O4 group. Second, we've identified a set of 4 fundamental spinors, but we'd like to see how to construct an arbitrary spinor of O4. Third, we want to consider the continuity and reality of our spinors, given that we're intending them to be terms in a harmonic expansion of root mod G. Fourthly and finally, we want to see how to understand translations in 3 space in the context of this model. Assembling our 4 basis functions into a 4-component multiplet, we see that SU2 left transformations represent weak isospin acting only on the left-handed doublet. There's a corresponding SU2 right group which acts only on the right-handed doublet. Any proper rotation of S3 which preserves the X4 axis acts equally on both doublets, and any proper rotation of S3 mixes the top 2 components and the bottom 2 separately, as pointed out by Janssen. To mix the 2 pairs of components, we need to consider parity. In 4-dimensional Euclidean space, this is an inversion of the hypervolume of the first 3 dimensions. By combining this with the SO4 group of proper rotations, we get the full orthogonal group. In angular coordinates, this inversion takes the form of increasing theta by pi and inverting theta tilde. Alpha is preserved. If each of the left-handed fundamental spinors has the same alpha dependence as its right-handed counterpart, then the induced action on the 4 spinor is as shown here. The doublets are swapped over, and then each is multiplied by I sigma 3. Fundamental spinors and higher order harmonics constructed from them form the basis for an infinite dimensional Hilbert space. Any single field configuration over S3 is an element of this Hilbert space. Within this, the fundamental spinors form a basis for a subspace. They are orthonormal under overlap integrals over the whole of the 3 sphere. Note that any complex multiple of a fundamental spinor transforms in the same way as the fundamental spinor. The coordinate dependence is carried in the fundamental spinor, not the coefficient. The arbitrary spinor of SO4 can therefore be written as a vector for which each component is a complex multiple of a fundamental spinor. We now know, at least in outline, why some of the harmonics in an expansion of root mod G must transform as spinors. Now, our spinors are complex functions, but root mod G is a real field. This has implications for the expansion. It may mean that the fundamental spinors we've found can only occur in the expansion in real combinations. At very least, it means that the products of the fundamental spinors on the 3 sphere with those on the 6 sphere can only occur in real combinations. It's also worth noting that the fundamental spinors we've derived have discontinuities. Even continuous combinations of them have discontinuous derivatives. This means that when we expand root mod G in harmonics, we have discontinuous fields in its expansion, or at least the derivatives of those fields are discontinuous. This sounds strange, but it should be remembered that no single coordinate system can be used across the whole three-sphere without discontinuities and/or degeneracy. Now, we're used to constructing our theories with three flat space dimensions. The spatial isometry group is then a semi-direct product of O3 and the three-dimensional translation group. We've got O3 transformations in our theory. How do the three-dimensional translations relate to the diffeomorphisms we've been considering? To answer this, we want to make a further change of coordinates on the three-sphere back to a set which have the dimensions of distance. We start by using the embedding of the three-sphere in R4 to find the coordinate basis for our set of angular coordinates. By taking inner products, we find that the metric is diagonal. That is, alpha, theta, and theta tilde are orthogonal everywhere. When all three angular coordinates are small, the first three x coordinates take these forms. We then define a new set of coordinates which take these forms everywhere that we can apply them. We then find that the basis for these coordinates is parallel to that for the angular coordinates, so that it's orthogonal everywhere, and approximately orthonormal around the origin. For points in R4 near the positive half of the x4 axis, SO3 rotates them around this axis, while transformations with this form move them outwards, taking them away from the axis. For small values of the parameters, this results in a simple displacement of the three y coordinates on S3 by an amount equal to the arc length traced out by the rotation angle omega I4. As the radius of the sphere is increased to infinity, the neighbourhood of the origin flattens out, the y coordinates reduce to x coordinates, and these transformations reduce to translations. We'll see this idea of rotations reducing to translations again when we look at the sixth sphere in more detail in the next section. Ideally, we'd like to do a similar analysis for the harmonics on the sixth sphere and to try to find explicit field configurations which transform as the two Spinor reps of SO6. I haven't begun this yet, but the explicit expressions for the harmonics aren't necessary to work out some of their most important features. We're still able to find out how the model evades the key no-go theorem for this kind of model, and find the relationships between the generators of the Spinor reps of SO6 and those of SU4, including those of colour SU3. Just as we considered the action of SO4 on the three-sphere and fields on it, we want to consider the action of SO7 on the sixth-sphere and fields on it. However, in doing so, we need to remember that the three-sphere and the sixth-sphere form a generalization of a torus, which can be embedded in a 10-dimensional flat space. For the three-sphere, the y-coordinates transform linearly under SO3, but non-linearly under the axial diffeomorphisms. Near the origin, these coordinates approximate to x1, x2, and x3. The sphere can be embedded in a subspace of R10, with these Cartesian coordinates together with x4. Similarly, for the sixth sphere, there will be y-coordinates which have an origin at a point on the sphere. These transform linearly under SO6 and non-linearly under the remainder of SO7. Near the origin, they will approximate to x5 to x10. The sixth sphere can be embedded in a subspace of R10 with these Cartesian coordinates together with x4. We now use the same considerations as we did for the three-sphere to find that rotations involving only omega 4x on points near the x4 axis act as a simple displacement on the y-coordinates. As the radius of the sixth sphere is increased to infinity, the neighbourhood of the origin flattens out, the y-coordinates reduce to x-coordinates, and these transformations reduce to translations. If our 6 extra dimensions were not compact, we'd have commuting translations with continuous spectra of quantum numbers. So Rafferty pointed out, these are not observed. It's the fact that the extra dimensions form a compact space that means this model evades O'Rafferty's no-go theorem. We can also find the transformations on the fields subject to a caveat using the theory of nonlinear realizations. The coordinates on the sixth sphere transform linearly under SO6, but non-linearly under transformations generated by T4x. In such a situation, we would normally multiply our field multiplets by a local T4x transformation in the corresponding representation. This would result in multiplets which transform linearly under the whole group. In our case, this would break the 8-spinor of SO7 into 2 4-spinors of SO6. We didn't go through such a field redefinition for harmonics on the 3-sphere because the spinors of SO4 are already spinors of SO3. It's not yet fully clear whether the field redefinition is required or appropriate here. Now, under any continuous isometry on the 6th sphere, there will be an induced SU4 transformation which maps the components of each 4-spinor into each other. There will also be an 8x8 version of the parity matrix which maps the two 4-spinors into each other. Generators of the SU4 can be written in terms of the generators of the spinor reps of SO6. These relations for the SU3 subgroup of SU4 generated by the first 8 generators, i.e. the Gell-Mann lambdas, are shown. Shortly, we'll see how we can identify this SU3 group with the color group of the strong force. We'd now like to see how the electroweak interaction arises and how the SU4 symmetry is broken. Some of the analysis in this section is very new, having been carried out since the last video was published. It's somewhat heuristic and incomplete and distinctly subject to revision. However, it's also potentially highly significant, so seems worthy of inclusion. We conclude with a brief consideration of electroweak symmetry breaking and a broad overview of unification and symmetry breaking mechanisms in covariant compactification. The key idea is to take as a background fermion field the one fermion which does not interact with any of the gauge groups, the right-handed neutrino. Under the extended isospin, that is chiral SU2 cross SU2, it has isospin up and is right-handed. It's clearly invariant under SU2 left. It's not invariant under SU2 right, but the U1 subgroup generated by the third generator simply changes the phase. Under SU4, it's the lepton state. In this case, it's invariant under the color gauge group, and the U1 generated by lambda 15 changes its phase in the opposite direction to that of the third generator of SU2 right. By scaling lambda 15 correctly, combined transformation under this and the third component of SU2 right will therefore leave the right-handed neutrino invariant. The generator of this combined transformation is precisely the expression we already have for weak hypercharge. So the idea is this. Say that a spinor of SO4 cross SO6 appears with non-zero coefficient in the harmonic expansion of root mod G in deep space. Then SU2 cross SU2 cross SU4 preserves the norm of this term. Indeed, it acts transitively on states with this norm. In this case, we can always identify the non-zero component with the right-handed spinor. With the right-handed neutrino. Perturbations from this background on the sixth sphere are up quarks of different colours, or corresponding modes in higher generations, related to each other by colour SU3. Perturbations on the 3 sphere are electrons and left-handed neutrinos, and combined perturbations on both spaces are down quarks. This appears to be a geometric version of dynamical symmetry breaking. Historically, there have been several examples of unified descriptions being developed of different force phenomena. The 3 listed here all took different approaches to unification. The mechanism used in the last of these, the Higgs mechanism, has often been assumed to be involved in any further unification. While it's true that this is the only one of these examples which involves symmetry breaking, drawing conclusions from a sample of one case is always risky. I've just given a fairly heuristic explanation of an alternative way that SU2 cross SU2 cross SU4 symmetry may be broken down to the standard model gauge group SU2 cross U1 cross SU3. And in the last video, I explained how the factorization of a 10-dimensional spacetime can be characterized. This also changes the symmetries which are manifest in the physics in a fairly complicated way. The GL10R group describing the changes of coordinate frames is broken, and the isometry group is also changed from a semi-direct product involving higher dimensional spacetime translations and rotations to a product of orthogonal groups. If we can incorporate the Higgs mechanism into this theory, then there are therefore actually 3 different mechanisms going on for what could loosely be termed symmetry breaking. Perhaps this helps to explain why it's been so hard to unify physics beyond the electroweak unification. This raises the question of how the Higgs multiplet can arise within covariant compactification and provide masses to the fermions. This is currently an open question in my research. However, it may be worth mentioning that a paper by Forgatz and Manton shows that in situations where a gauge field is required to be symmetric under a compact group of spacetime transformations, its field strength can contain scalar fields with quartic potentials. Manton then used this theory to show how the Higgs doublet, with its famous Mexican hat potential, could arise in a higher dimensional theory. Whether their analysis could be adapted for covariant compactification is far from clear at present. And there are plenty of other outstanding questions, including why SU2 left cross U1 is broken, but not SU3, and what the dynamical implications are of the breaking from SU2 cross SU2 cross SU4 to SU2 cross U1 cross SU3.